Hey everyone, and welcome to another AP Calculus video. Today we're going to talk about related rates and how we solve these problems. Now basically this involves taking, if you think about in math, that typical math problem where we talk about one train leaves Chicago and one train leaves Los Angeles and all this stuff is happening in the middle where they're going to meet, that sort of a thing. This is the type of problem that we're going to solve today. And so before we get into solving an actual related rates problem, let's kind of, look at what's involved. So here's an example of a typical problem that you might find on an AP exam or on a calculus test. It says this: water runs into a conical tank at a rate of 9 cubic feet per minute. So you're going to get some information about something happening in real life. And it's always related to time. So, well, maybe not always time, but most often it is related to something changing over time. And so then it says the tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Now, this is not your typical, how fast is something changing type of problem, because if you think about this, if you have a conical shaped tank, what happens is the height is going to be changing at a different rate depending on where in the tank you are. In the beginning, there's not as much volume down at the bottom. It's got a smaller radius to fill. So if the water is going in at a constant rate, the height is going to grow the fastest at the bottom. But then as the tank gets wider and wider, and you have a wider space to fill, that same amount of water is going to fill up more space laterally than it is with regard to the depth. So the depth of the water will change faster at the bottom where the radius is smaller, and it'll change slower at the top where the radius gets larger. So this is where we run into trouble. And so what we do is we relate everything to time. Time is the constant. And so here are the basic steps that we are going to eventually solve this problem using. It says this: step one, we're going to draw some sort of picture, and we're going to get to that. Step two, we're going to make a list of all the information we know. Step three, we're going to write down what we want to know. So what is that missing piece and what are we trying to find? Then we're going to find an equation, or maybe a couple different equations that will relate all the information that we're given. And then finally, we're going to differentiate the equation that we have with respect to time. Now, that's the step that is going to be new for us right now, is differentiating with respect to time as opposed to differentiating an equation with respect to x. So we're going to walk through that before we can solve, and then finally in step 6, plug some values in and solve for the missing unknown piece. We're going to look at what it means to differentiate with respect to time. So let's take a look at a couple of, equations and examples of what we would do. Now, when we differentiate with respect to time, let's think back to what we learned way back in Unit 3 where we talked about differentiation and finding derivatives, and we did this process called implicit differentiation. And in implicit differentiation, we were differentiating everything with respect to x. And so when we would come across a variable that was not x, we treated it as an internal function of x. And so we had to apply the chain rule. So that's essentially what we're going to do here, except the variable that we're differentiating with respect to is time. It's not a variable that exists in the equation. So you can see in every single one of these, there is no time variable. They're all, typical geometry formulas or some other typical formulas that we've seen before. And so it's going to be a little bit different because every single variable is going to be treated as an internal function of time. So we're going to basically put a dA dt, a ds dt, a dp dt, a dl dt, a dw dt, and so on and so forth. We're basically going to be putting so many different derivatives, and we're going to apply that chain rule to every variable. And it's going to look like this. If we take the area of a square and we try to differentiate this with respect to time, basically, the derivative of a is just 1, but we're going to throw dA dt in there. The derivative of s squared is 2s, but we're going to throw in a ds dt. So we've just differentiated with respect to t. So that's it. So let's try this other one, perimeter. The perimeter function, when I differentiate this one with respect to t, the derivative of p is just going to be dp dt. And then the derivative of 2L is going to be 2 dL dt. It's the derivative of L with respect to t, plus 2 dw dt. Now if you think about this, we're already doing this when we differentiate an equation. So if we had like y equals x squared, the derivative of y is dy dx, and then the derivative of x is 2x. But we don't need the dx dx because dx dx is just 1 and it would just go away. So really essentially we're already doing this process. Now we're doing it to a degree where it's very obvious that we're doing it. So let's keep going. The Pythagorean Theorem. This is one that'll show up in a lot of our related rates problem. So we'll have 2a, but we'll throw in a dA dt plus 2b dB dt plus 2c, or equals 2c dc dt. So it's all about just putting in that d dt of whatever variable we're working with. Let's keep going. We've got the area of a rectangle. Now this one is a little tricky because we will have to use the product rule. And it'll look a little bit like this. We'll have dA dt equals, now we're going to do the first, which is L times the derivative of the second, dw dt, plus the second times the derivative of the first, dl dt. So the product rule still applies. Even when we're doing differentiation with respect to time, we're still going to apply that product rule. Let's keep going. The derivative of tangent. Ooh. Well, we're going to remember our pst, right? Pst, P-S-S-T. So the derivative of tangent is secant secant, or secant squared. So we're going to have secant squared theta. But remember, we're differentiating with respect to t. So the chain rule says do the derivative and then d theta dt. And we're going to have to use the quotient rule here for x and y. So we're going to go low, d high, that'll be dx dt, minus high, d low, that's dy dt, all over low squared. So we can differentiate using the product rule, using the quotient rule, using trigonometry, but every variable needs a d dt for that variable. Let's do this last one here. This one says find the volume, differentiate this one with respect to time, but we're going to give you a little extra piece of information. We're going to tell you that r is equal to h over 2. Now, you're going to find that having so many variables is not preferable. We don't like to do the product rule. We don't like to make it difficult on ourselves. So what I'm going to do is, if I ever have a relationship where it says r equals, some expression in terms of one of the other variables, I'm going to replace that first. And so I'm going to rewrite this. I'm going to have 1/3 pi times h over 2 all squared h. And then I'm going to simplify 1/3 pi, and then this will be h cubed over 2. And I'm going to simplify one more time to pi over 6 h cubed. So there's my volume equation. That's what I'm going to differentiate with respect to time. So it'll look like this. dv dt equals, now the derivative of this, I would multiply by 3. I'd get 3 pi over 6, which will reduce to pi over 2, h squared dh dt. So I'm going to stop there. I'm not going to simplify any further, but that would be how I would differentiate this equation with respect to time, especially if I'm given a variable in terms of one of the other variables. It makes it easier on myself. So now let's actually solve a problem and see what's involved. And again, this is just an introductory video. For related rates, we're going to be doing basically one problem per video, and there's a lot of different types of problems and typical ones you're going to come across. This particular problem with the water running into a conical tank is a pretty common type of problem, and so we want to make sure that we're breaking it down and kind of generalizing with these problems so that when you see something similar, you're ready to go. Let's take it step by step. We're first going to draw a picture. So I have my conical tank. It's upside down. It's point down. So here we go. There's my conical tank. So the water is flowing in at 9 cubic. I'm not going to put that in. The only things I'm going to label here are things that are constant. So like the height of the tank isn't going to change, right? The tank stands point down and has a height of 10 feet and a base radius of 5. So like these things aren't going to change. What is going to change is the water. Anything dealing with the water is something that is not a constant rate. So I'm going to just draw an arbitrary water line. And these I'm not going to label with numbers because, again, those numbers are changing. But if this is my water in the tank, we'll highlight it blue so it stands out. If this is my water in my tank, I know that the water is changing at a rate of 9 cubic feet per minute. So this is step 2, making a list of all the things we know. So what do we know? We know that the water is changing at a rate of 9 cubic feet per minute. So I'm going to go ahead and I am going to write that down, dW dt. So this is a rate. The rate of change of the water is 9 cubic feet per minute. I'm going to include those units. So let's see. The base radius is 5. How fast is the water level rising when the water is 6 feet deep? So we know what we want to know is how fast. Anytime it's talking about how fast, that's a rate. So I want to know dH dt when, there's always going to be a when clause. So at this instant, when the water, so we're going to call that H, is 6 feet deep. So I'm going to come back over here. I'm going to label on my picture. I'm going to zoom in a little bit. I'm going to label this H, and I'm going to label this R. Even though the radius of the base is 5, that's not a variable. It's not changing. But the radius of the second cone, the cone of water, is going to be changing. And that is something that's going to be, you know, that's going to be something that changes. So let's take a look at what we have. We know how fast the water's going in. We know the height and the radius of the tank. That's a constant. We know that the water level is changing. H and R are changing. We want to know dH dt when H is 6. We know the water is going in at 9 cubic feet per minute. The one piece of information I don't have anything about is R. So as you're setting these up, you want to notice we've got 2 variables happening here with our cone. And I only know information about the height. So that's going to present a problem as we move forward. So let's see if we can identify the problem as we write a few more things down. So we did step 2, we made a list of all the things we know. We did step 3, we write down all the things we want to know. Now we need to find an equation to relate them. Now our equation here needs to deal with the volume of this cone because it's dealing with a volume of water. So the volume of a cone is 1/3, pi r squared h. And this should look familiar because we just did a problem involving this. Now, there's my r, there's my h. And here's the thing. I don't want to have to do the product rule, number 1. Number 2, I don't have any information about the radius, other than I know that the radius of the cone itself is 5. And so I'm going to run into trouble if I try to, I can differentiate this, but I'm going to run into trouble here in step 6 because it says plug in the values from step 2. There's going to be an r in my equation, and if I have nothing to put in for r, then I'm going to run into trouble. Furthermore, I've labeled this volume V. So what I'm going to do is I'm going to go up here, and where I said dW dt, I need to understand that this W is actually the volume. So I'm going to rewrite this as dV dt, where V is the volume of water. All right, I've made a note, made an adjustment. Now I need to write down some other things. Now there's some hidden information in this problem, and this is typical to these area models and these like volumes of conical tank problems. And it's not unusual for there to be hidden information and hidden bits of ratio information. And here's what I'm talking about. You'll notice we haven't done anything with this information. And when you look at the cone of water, what I want you to notice is that it is a similar geometric shape. Now, when we have similar geometric shapes, that means that the sides and the heights and all of the dimensions are going to be proportional. And so what we have here is a situation where if I take H, and that's the height of the water cone, and put it over 10, h is to 10 as r is to 5. And so I have this proportional geometric similar shape. Similar shapes have proportional dimensions. So, knowing this, I can actually replace r with something equivalent. And so what I want to do is, because I have no information about r other than the radius of the cone itself, of the tank itself, I'm going to solve for r here in this proportional relationship. I'm going to multiply both sides by 5, and I'm going to get h over 2 equals r. Now, this should also look familiar because we just did a problem like this. I'm going to replace r with this equivalent statement, and it's going to look like this. V equals pi over 3 times h over 2 squared h, which turns into pi over 3 times h cubed over 4, which is pi h cubed over 12. And looking back, I think I may have actually made a mistake earlier on. Let's double check. Did I make a mistake here? I sure did. This should have been a 4. Did you catch that mistake in my video? Yeah. So this should have been a 4, making this a 12. And it is essentially the same exact problem that we had before. So now let's go back, now that we've adjusted and fixed our mistake. Let's go ahead and differentiate with respect to time. So dv dt so we get pi over 4 h squared, and then dh dt. We're going to toss that in there. Can't forget that. That's pretty essential. And so now we have this differential equation where we can now take the information that we know from above and put it in. So I'm going to zoom out so we can gather that info. And here's what we're going to do. We know that dv dt is 9. And this is all information about an instant in time. And that instant is when h is 6. So we have an h. We want to make sure we have all the info we need. We have a dv dt. All of our variables are now covered. We want dh dt. That should be the only unknown left that I don't have information for. So now I'm going to go back and plug things in. dv dt is 9. We're going to let h be 6. And we're going to solve. So 9 equals pi over 4 times 36 dh dt. So 9 equals 9 pi dh dt. And when I divide, I'm going to get 1 over pi equals dh dt. This is the rate of change, and we're going to make sure we include units. So it says here we're dealing with feet and cubic feet per minute. So h is a linear function, so it's not going to be cubic feet. It's going to just be feet, so it's changing at this. So we're going to say 1 over pi feet per minute is what we are increasing by. It's a positive value, so we're increasing. So this is a basic related rates problem, and again, we drew our picture, we wrote down what we wanted and what we needed. We looked at our image and gathered some information to try to reduce our variables. We differentiate with respect to time, and then we plug in the information we know and solve for what we want to know. And this is essentially the breakdown to how we solve a related rates problem. The key being, of course, that we're differentiating with respect to time. And there will be several more videos to follow, each one focusing on a different type of problem that you're going to come across. So make sure that you watch those additional videos to see the various different types of related rates problems that could come your way. But no matter what, I want you guys to remember that as tough as this might seem in the beginning, you're going to get there. It's going to be okay. You can do this. You've got this.